Okay, on this quiz you were given this weird looking function. It's not really one function, it's a family of functions that depend on some parameter a. So f sub a is a different function for every different value a. But in any case, you're asked about the limit as x approaches, not negative 1, just 1. Limit as x approaches 1 of f sub a of x. And the question is, does this ever exist? So let's explore this. So first things first, if we actually plug x1 into this formula. So remember, this is how we find limits. The first thing you do, step 1, is always you just plug in the value into the formula. So you get 1 squared is 1, plus a times 1 is just a, plus 3 times 1 is 3, plus 3a. All over, what happens when we plug in a 1 on the bottom? You get 1 squared is 1 plus 2 minus 3. So wait, 1 plus 2 minus 3, that's 3 minus 3, that's actually a 0 on the bottom. Alright, so now, are we in a type A? Type B, well, type B was piecewise, and I don't see anything piecewise here. And also, I don't see any absolute value, so it's not a hiding piecewise problem. So it's definitely not type A on type B, but it might be type A, type C, or type D. So we were dividing by 0. It wasn't just some pretty simple finite value, so it's not type A. So the question is, do we have a type C problem or a type D? And remember what those are. Type C is when you have 1 or anything not equal to 0 divided by 0. Type D is the indeterminate form. Things like 0 over 0 or infinity over infinity or so on. So here, do we have a 0 over 0 or a 1 over 0? I mean, I have a 0 on the bottom, but what about this numerator? So then the question is 1 plus a plus 3 plus 3a. Is that equal to 0 or not? Because if it's 0, then it's an indeterminate type problem, and we have to do some more calculation, some algebraic manipulation to simplify it. But if it's type C, if it's a finite number, this numerator is not 0, then it's going to be an infinite asymptote. So we can think about these things separately. So is this equal to 0 or not? Well, obviously, just looking at it, it depends on what the value of a is. For most values of a, this isn't going to be 0. But what you'll notice is, if you just kind of solve for a, this is just, I mean, you could combine the 1 and the 3, and that's a 4. Combine the a and the 3a, and that's 4a. So we want to know, when would this be 0? Well, clearly when a is equal to negative 1. So what we see is that for f sub negative 1, when a is negative 1, this is going to lead to a type D problem. It's going to give us a 0 over 0. But for, it's going to give us a type D. But for fa, where a is anything not equal to negative 1, we're just going to have a type C problem. It's going to be an infinite asymptote. So the problem doesn't really ask us to explore whether it's a positive infinite or negative infinite asymptote, or whether it depends on you're coming from the left or right. It doesn't ask us about that, really. It just wants to know, is there any value for which the limit actually exists? Like, it's a finite value. And the only shot we have is this one. Here we know that it's either going to go to positive or negative infinity, or it's going to do one from the left and the other from the right. But it's definitely going to have a vertical asymptote, and it's going to shoot off to infinity. It's not going to have a finite limit. But as for this case in type D, who knows what happens after the algebraic manipulation? Maybe it does come to some finite value. So let's actually explore this. What does f sub negative 1 look like more specifically? If we actually plug a negative 1 into the original formula, f sub negative 1 of x is equal to x squared. Now that a is negative 1, so that's actually minus x. That's plus ax. 3x doesn't depend on a, and then we're subtracting 3 over x squared plus 2x minus 3. Okay, well, what do you notice? You have x squared, you have minus x plus 3x makes for 2x. You have 3 things, you subtract one of them, you got 2 left, and you have a minus 3. Do you notice that now the numerator simplifies plus 2x, and it looks exactly like the denominator. They cancel, and you get 1. Don't make a silly algebra. They don't disappear into nothingness and become 0. The top cancels the bottom, you get 1. Something divided by itself is equal to 1. Now, technically, if I'm going to be absolutely correct, it's not even defined wherever the denominator is 0. So at the value 1 and, I don't know, -3, I think, it's not even defined. But everywhere else, it just looks like this constant function 1. So now we take the limit. The limit as x approaches 1 of just 1 is just 1. I mean, it doesn't even depend on x. So, checks out. So what we've noticed here is, just to recap, when we actually plugged in values, we didn't know what kind of type of problem we had, because we had a 0 on the bottom, but whether the numerator was type C or type D depended on the value of A. It was going to be a type C, which means vertical asymptote infinite limit for all values of A except -1. F sub -1 was the only thing we had a chance of being a finite value, and we just checked it. We plugged it back in, everything canceled, it was equal to 1. So in the language of a previous video, our algebraic manipulation turned the type D problem into a very simple type A problem, where it was just continuous. Alright, so that's how you would handle that problem. Now, what happens as we approach -3 this time around? Alright, so what you'll notice is, and I think it would just be helpful, right from the get-go, can we just factor this guy? That's a wise thing to do. I'm getting tired of writing it out. X squared plus AX, 3x plus 3a, over, now the bottom, x squared plus 2x, what multiplies to -3 adds to 2? Well, I think 3 and -1 do. So the bottom is x plus 3 times x minus 1. Alright, so as you plug in a -3, obviously the bottom is going to be 0. This term is going to be 0. So we are going to divide 0. Our first inclination now is to just plug in the value of -3 for x. And what do we get? If we actually plug in the value of -3, well, you get 0 on the bottom, like we just said. You're going to get -3 squared is 9. Right? Times a is going to be minus 3a. Right? The x is now -3. Plus 3x is, well, but x is -3, so it's actually not plus, it's minus 9, right? 3 times x would be -9, so that's minus 9. And then we just have a plus 3a, and you'll notice, cancel, 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 cancel. We just got 0 over 0. We are already in a type D problem, and it doesn't even depend on the value of a. We are always in a type D problem, because we always got 0 over 0. Alright, so there ought to be some algebraic manipulation to this guy. So, do we find common denominators? Not. I mean, it's all one fraction. There's no separate fractions. So when in doubt, factor out. That's your mantra for this. So we've already factored the bottom. I wonder, can we factor the top too? Well, let me see if I can factor an a out of 2 of these terms. I have an x squared term lying around, and I also have a 3x term lying around. But then I have ax and 3a, so isn't that the same as plus a times x plus 3? So I factored out an x plus 3. And actually, now that I do that, I can tell, hey, wait a minute, don't I have an x plus 3 hiding in that? Isn't that x times x plus 3? So isn't this the same as x plus 3 times x plus x plus 3 times a all over all that denominator? And then, hey, wait a minute, now I can factor out the x plus 3. That's x plus 3 times x plus a, isn't it? Divided by x plus 3 times x minus 1. And look at what happens. They cancel. And we're just left with x plus a over x minus 1. And now, alright, so we've simplified it algebraically. So now let's plug in again. Negative 3. I hope something even easier works out. So if we plug in negative 3, what do we get? Negative 3 plus a divided by negative 3 minus 1 is negative 4. So we get this answer. Is this type A, type C, type D? Well, you don't have a 0 on the bottom, so it's not type C. It's not in 0 or infinity. It's not type D. This is a simple type A problem. This is a finite value. For any value of A, this is just some simple finite value. So there we go. So it actually doesn't matter what value of A we pick. We always ended up with a type D that we could algebraically simplify into a type A problem. So the limit always exists and is equal to negative 3 plus whatever that A happens to be divided by minus 4.